let's try to compute a few simple Laplace transforms. How do we compute the Laplace transform of the zero function? Well, I claim that's just zero, and we can see by definition here, the Laplace transform of zero is just going to be the integral from 0 to infinity of e to the minus st times the zero function dt. Well, of course, that makes the integrand 0, and that will just be 0. Now, when I write this, remember, this is the zero function with variable t, and this is the zero function with variable s. So they're both written just as 0, but think of this as a function of t and this output as a function of s. What can we say about the Laplace transform of the simple function, which is the constant 1? Well, that's just by definition the integral from 0 to infinity of e to the minus st times the constant function 1 dt. I've already written the answer here, 1 over s, but let's see that computation. How do you integrate from 0 to infinity e to the minus st? We've kind of seen that before. dt, that's just a limit. I can't use t here, that's because I'm using t differently, so I'll use b as b goes to infinity of the integral from 0 to b of e to the minus st dt. To integrate e to the minus st, I have minus 1 over s e to the minus st, integrated, evaluated from 0 to b like that, and I want the limit as b goes to infinity. And when I plug in b, I get minus 1 over s e to the minus sb. And then I subtract what I get when I plug in 0, which is just plus 1 over s. And here I should have been clear, as long as s is greater than 0, this will tend to 0 as b goes to infinity, so the value will just be 1 over s. That's true if s is positive. If s is negative, then that blows up. So the Laplace transform of the constant function 1 is this function 1 over s when s is a positive number. How do we take the Laplace transform of an exponential function e to the at? Well, that is by definition the integral from 0 to infinity of e to the minus st times e to the at dt. We just integrate e to the minus, I'm going to rewrite that as minus the quantity s minus a times t, that's this product here. And that integral is exactly the same as this one, only we're using s minus a in place of s. So that's just going to be 1 over s minus a, as long as s minus a now is greater than 0, which is the same as saying s is greater than a. So I'm just piggybacking off of this previous computation, and instead of putting an s there, I have an s minus a there. Now, in order to talk about Laplace transforms for more complicated functions, we want to use the idea that the Laplace transform L is a linear operator. And this is now a bit complicated to express, but it's a linear operator on what space? The space that consists of all functions f, which have the appropriate boundedness conditions that we talked about. So this is on the space of functions f of t, where the absolute value of f of t is bounded by some constant k times e to the at for t greater than or equal to some number m, and f is piecewise continuous. Continuous on 0 to a for all a greater than or equal to 0. So if you look at the space that consists of all functions of this form, L is a linear operator on that space. And what does that mean? That means when you take the Laplace transform of f1 plus f2, that should give you the same thing as the Laplace transform of f1 plus the Laplace transform of f2. Is this obvious? Well, the Laplace transform of f1 plus f2 is just the integral of e to the minus st. I did not write that correctly here, so let's try that again. E to the minus st times f1 of t. I'm sorry, for the Laplace transform of f1 plus f2 is the integral of e to the minus st times f1 of t plus f2 of t, in parentheses like that, dt. That's the Laplace transform of the sum. And just by basic properties of integrals, which extend to improper integrals very easily, that's just the integral of e to the minus st times f1 of t plus the integral from 0 to infinity of e to the minus st f2 of t. And that's just exactly the Laplace transform of f1 plus the Laplace transform of f2. The second property we need for linearity of this operator, that's property 1. Property 2 is that the Laplace transform of a constant times f should be that constant times the Laplace transform of f. And I want to leave you guys to just see if you can formally write down why this is true. Basically, just write down how this Laplace transform is defined, pull out the constant c, and you get that. What does linearity get you? It says you can thus take the Laplace transform of any linear combination of functions, and it's just a linear combination of those Laplace transforms. So what if I want the Laplace transform of the function 1 plus e to the t? Well, that's just the Laplace transform of 1 plus the Laplace transform of e to the t. Now, what was the Laplace transform of 1? That was just 1 over s. We computed that before. What's the Laplace transform of e to the t? That's just 1 over s minus 1. What if I want the Laplace transform of 4 plus 3 e to the 2t? Well, you can see already, and you can do this easily in your head, the Laplace transform of 4 is just 4 times the Laplace transform of 1. So we have 4 over s. Laplace transform of 3 e to the 2t is just 3 times the Laplace transform of e to the 2t, which is 1 over s minus 2. I want to talk about a couple more examples where you'll start to see now how we can do more fun things with the Laplace transform. Let's look at this function u sub 3 of t, and we're going to be talking about these in section 6.3 quite a bit. This is a step function, a standard step function, whose graph looks like the following. We want u sub 3 of t to be is defined to be 0 if t is less than 3. So here's 3. The function has a graph. Here's our t-axis. Here's our y-axis. So the function's graph is 0 all the way until you get out to 3, and then it jumps up to 1. And we put the value there. So there's a hole here, and it jumps up to there, and the graph is 1 like that. So the graph is 0 here, and then it jumps up to 1. Can we take the Laplace transform of such a discontinuous function that has a single jump discontinuity here at 3? Well, the answer is yes. Integration has no problem with that. How do we integrate from 0 to infinity e to the minus st times u sub 3 of t? That's the Laplace transform of u3. Well, we can write that as the integral from 0 to 3 of e to the minus st u3 of t dt plus the integral from 3 to infinity of e to the minus st u3 of t dt. And notice that between 0 and 3, this is just 0. So that just is trivial. And then we we integrate from 3 to infinity. I'll write that as a limit as b goes to infinity of the integral from 3 to b of e to the minus st times u3 of t. But now u3 is just 1. So we have this integral. And that's equal to 0. Well, I'll stop writing the 0. That'll make things easier. That's just equal to a limit as b goes to infinity of anti-differentiating the e to the minus st, we get minus 1 over s e to the minus st from 3 to b. When we plug in b, we get minus 1 over s e to the minus sb, and then we subtract the negative, which gives us a plus e to the minus 3s over s. And now as b goes to infinity, this part goes to 0 as long as s is greater than 0, and we just are left with e to the minus 3s over s. And it's important that s is bigger than 0 for this part to tend to 0. So we can take a Laplace transform of this standard sort of step function in a very simple manner. And what can we do with that? Well, let's say I want to flip this step function around and ask, what about this function f of t, which is 1 when t is less than 3. So here's 3. I want the graph of y equals f of t to look like this, where it's 1 until you get out to 3, and then 0 everywhere else. Well, of course, it's really not a problem for you to compute the integral directly, to compute the Laplace transform of f. But we don't even have to do that, because f is just exactly 1 minus u sub 3 of t. If you just take 1 minus this function u, you get exactly this function f. So that's just the Laplace transform of 1, which is 1 over s, and we subtract the Laplace transform of u sub 3 of t, which we just computed. And there we have the Laplace transform of the function f.